Okay, hello everybody. Thank you very much for attending this talk, and thank you for the opportunity of giving the talk. Okay, so we heard about 21 centimeter cosmology and about the 21 centimeter signal from the early universe, and in particular the efforts from the Lucy Knight mission that will do these radio measurements at low frequencies from the far side, hopefully leaving for the moon next year. So here I wanted to go back to that science. And well, first of all, this slide reminds you of the signal we are after, the global 21 centimeter signal, which is the sky average version of the 21 centimeter signal as a function of frequency, which corresponds to the evolution of the universe as a function of time. And the main two features that we want to detect and characterize with instruments from the moon are the two absorption troughs that you see here between 0 and 50 megahertz and between 50 and 100 megahertz. The first one is an absorption trough coming from the dark ages before the formation of the first stars, and the second one comes from the cosmic dawn during the formation of the first stars and galaxies. Okay, but it's great that Lucy Knight will conduct observations from the moon at these frequencies. We want to also look beyond that. And the main message I wanted to communicate here is that an ambitious program to observe the dark ages and the cosmic dawn from the moon should include both, at least, lunar landers as well as orbiters. This signal is extremely difficult to detect, and we should leverage the complementarity between landers and orbiters. So here I'm gonna give two examples on how landers and orbiters are complementary and why we need both, in my opinion. So Lucy Knight will be a lander, and as an example of an orbiter, here I'm showing their mission. Maybe some of you know about this mission. This mission was proposed about a decade ago and was PI'd by Professor Jack Burns from CU Boulder. Okay, so what is the best example to give in terms of complementarity between landers and orbiters? Well, the dark ages requires observations below 50 megahertz, and the center of the dark ages feature is at 18 megahertz, okay? And at that frequency, the sky has a brightness temperature of about 150,000 Kelvin, but the signal we are after is 40 millikelvin, okay? And so the question is, to have a signal to noise of 2, in other words, to have a noise level of 20 millikelvin, for how long do we need to observe? Okay, so here I'm using the radiometer equation to estimate that. I'm using a frequency bandwidth of 1 megahertz, and I'm asking the same question for the cosmic dawn. The center frequency of the cosmic dawn signal is roughly 75 megahertz. Well, at that frequency, the sky is 305,000 Kelvin nominally, okay? To have a noise level of 20 millikelvin, which would correspond to a signal to noise of a few, and using the same frequency bandwidth, for how long do I need to observe? And so here are some parameters that I'm including in this estimate are, well, the observation time, of course, but also how many antenna polarizations I will be using. And here, as an example, I'm using just 2. In other words, if I observe the sky with a cross dipole, similarly to Lucy Knight, okay? Okay, so another parameter that is important in this discussion is the observation efficiency. How efficient during 24 hours, let's say, how much of that time will I gather data through, essentially? Something to consider when estimating the efficiencies is the contribution from the sun. On this slide, I show, well, it's from the paper you see at the bottom, but what I'm trying to highlight is the fact that the sun, which are the yellow lines in this plot, can have contributions across a wide range of orders of magnitude relative to the radio sky, to the galactic background, which is typically the dominant contribution at lower frequencies. So the sun contribution can be lower than that typically, but if the sun is very active, it can be higher than the galactic contribution. So do we want to use data with galactic contribution for cosmology analysis? If the answer is no, that means that our observation efficiency will be lower, okay? So this is an important factor in our calculations. So in this table, I summarize the findings using nominal values for efficiencies. And the bottom line is that if we want to detect the dark ages signal with a signal to noise of about 2, with a lander, in the best case scenario, we need to observe for a year, okay? If we have a lower observation efficiency of 50%, if we only observe during nighttime, lunar nighttime, then the observation time goes up to 2 years, okay? With an orbiter, because the orbiter spends less time on the night side of the moon, the observation efficiency typically would go down. And in that case, we are talking about many years of observations to reach the signal to noise required for detection. For the cosmic dawn, in contrast, we need to observe between hours and days to detect the cosmic dawn signal, either with a lander or with an orbiter. It tends to be better with a lander because your efficiency tends to be higher. Okay, so the cosmic dawn signal can be detected with a lander or an orbiter. The dark ages signal is better with a lander. The orbiter will force us to observe for years longer. Okay. Other effects that in which these two approaches differ have to do with the moon itself. The surface temperature of the moon affects the performance of a lander sitting on the regolith, right? The temperature effects are different on an orbiter. And so the instrumental performance and stability will be different between the two. Other effects have to do with the brightness temperature of the regolith itself. They will affect differently a lander sitting right above the regolith versus an orbiter kilometers away from the surface of the moon. And another effect has to do with the electrical parameters of the regolith. They will affect the antenna beam of a lander, as Stuart mentioned, but they will not affect directly the antenna beam of an orbiter because it's too far away. However, the electrical parameters of the surface of the moon will affect measurements with an orbiter anyways, just differently, okay? So, okay, this plot shows the stability of the surface of the moon in terms of temperature at nighttime. So the green line shows the stability of the temperature during lunar night. It is between 100 and 150 Kelvin, but it can go as high as 400 Kelvin during the day. So this reason alone might force you to restrict your observational efficiency, okay? The brightness temperature of the moon, it has a dependence on the physical temperature of the moon in general, but at lower frequencies, at radio frequencies, it tends to be more stable because the brightness temperature comes from deeper regions in the regolith, and those regions are not affected directly from solar radiation. So we need to know ideally what this brightness temperature is and include that in the calibration of our instruments. Now, this brightness temperature will affect landers and orbiters differently. So in both cases, we need to know this quantity, but it will affect the two types of missions differently. Now, going back to electrical parameters of the soil, Stuart mentioned that for a lander, they impact directly your beam and impacts the beam as that points to the sky, and it impacts obviously the beam that points toward the regolith, and it adds a frequency structure in the beam that you do not want. Okay, but at least you need to know what that structure is, and to know what that structure is, you need to know what the soil parameters are. So we need to estimate these parameters with high precision and accuracy for a lander in particular, because it affects the beam.
1 minute.
Okay. Now, for an orbiter, the electrical parameters do not affect directly the beam, but they affect how much galactic radiation gets reflected off the lunar surface, okay? I'm sure you know that electromagnetic gets reflected according to Fresnel equations. And these equations depend on the impedance of the media that we are talking about. In this case, the relevant medium is the lunar regolith. And to compute what this parameter is, this reflection coefficient or reflectance, we need to know the electrical parameters of the regolith, the conductivity and permittivity, okay? And these parameters, we know from current measurements that they can vary by factors of a few, as a function of space and as a function of depth, as a function of density of the lunar regolith. So we need precise information about these parameters for both cases, orbiter and lander, but they affect the observations differently in ways that are complementary. Okay, so in summary, the landers and orbiters have strengths, challenges, and requirements that are complementary for the observations of the global 21 centimeter signal. Some factors to consider in the mission's design include the integration time or observational efficiency, the temperature stability, which you need to account for during calibration, the thermal emission from the moon, and the moon's electrical properties. The more information we have about this, the better. And an ambitious program to observe the dark ages and cosmic dawn from lunar environment should include both landers and orbiters, and we have to leverage their complementarity. Thank you very much.